Well, welcome to Lecture 19 in Topology. This is on projective spaces. I'm following sections 5.3 and 5.4 of Manetti, which presents projective space as a quotient space corresponding to a particular partition of the space by homeomorphisms of a particular type. So, actually, it does a lot of things. I think if you take a step back and look at it at the end of it, it's given about 2 or 3 different ways of defining projective space, and it just mostly is talking about how to get from one version of it to another. But anyway, so to start with, homeo X is the set of homeomorphisms from a topological space X to itself. So it's a group because the composite of homeomorphisms and the inverse of homeomorphism is once again a homeomorphism. And of course the identity map on a space to itself is a continuous map with continuous inverse, so it's a homeomorphism. And so in fact, the set of homeomorphisms over a topological space forms a group under the composition of functions. Now usually it's a pretty huge group, but there are subgroups that are particular interest that are finite, so we'll be focusing our attention mostly on, well, I guess they're not necessarily finite, but certainly there are some finite ones we'll look at. But anyway, they're not so huge as to be hard to understand. Let's see here. Given a subgroup of homeomorphisms, then you can define equivalence on the space to be whether or not the 2 points are connected by the action of some homeomorphism in the subgroup. And so this forms an equivalence relation, and the equivalence classes are known as G-orbits. And the set of equivalence classes is X mod G, like that. And so this X mod G is basically a set of equivalence classes for this equivalence relation. Now, let's see here. Excuse me. So, I merged sections 5.3 and 5.4 together because most of the technical points in 5.4 are just relying on like the propositions in 5.3, so I thought it'd be helpful to just have them all together in one discussion. So here we go. If G is a subgroup of homeomorphisms, and you let pi be the usual mapping from X to the equivalence class of X, the canonical, we're going to call it the canonical quotient map, then pi is an open map. And if G is a finite group, then pi is also a closed map. So the proof is here. So, and it has to do with the definition of quotient topology again here. So let's see here, we take A, a subset of X. The inverse image under pi is the union of G-orbits, which look like this. Let's see here. So pi inverse of pi of A is the union of, the image under G of A, where G is a homeomorphism in that group, right? And so that's but the thing is, if A is open, right, then G of A is open because G is a homeomorphism, so G homeomorphisms are open maps, they take open sets to open sets. And then this would be a union of open sets, which then means that pi inverse of pi of A is a union of open sets. And which means it's open. And then by the definition of quotient topology, pi of A is an open set because it's an inverse image of this. Anyway, by the definition of quotient topology, pi of A is open. Anyway, so then if G is finite, then the argument above still holds, replacing open with closed, but then it's a union. Well, see, this would be an arbitrary union of closed sets if we didn't have the finite condition. That's where the argument would break down for arbitrary possibly infinite dimensional groups. But in a finite group, then this is a finite union. So it's, again, closed. And remember, in the quotient topology, the closed sets are exactly the ones that appear like that. So, all right, anyway. If you're rusty on the quotient topology, probably be a good idea to go back and look at it again. Let's see here. So let G be a group of homeomorphisms of X, then the quotient X by G is Hausdorff if and only if the set K is closed in the product. So K is the set of X, and then this is basically just saying X and Y such that Y is equivalent to X under the G-orbit equivalence. And yeah, so the proof of that is down here. Let's see here. See, the map isn't. That's first of all, it's an open surjection, so you can define P from the Cartesian product of X and X to the Cartesian product of the quotient of X by G with X by G, the product of those, right? And then, so since it's the fact that pi was open makes P open, so you have an open map from here to here that makes it an identification, right? So an open surjective map is an identification. Not every identification is that, but certainly if it is open and it's surjective, it's an identification map. And then if we have P of xy is in the diagonal of X by G, that's going to be true if and only if X is equivalent to Y, because remember that two equivalence classes are equal if and only if they have the same, if their representatives are equivalent, which is to say that X is related to Y like that, X is equivalent to Y, but that's exactly saying that X is equal to, Y is equal to G of X for some G in the group, which is what it takes, of course, for XY to be in K, which means that the set K is exactly the inverse image under P of the diagonal of the quotient of X by G. And since P is an identification, that makes the diagonal, that makes this diagonal closed if and only if K is closed, all right? But we know that the diagonal of X by G is closed if and only if X by G is Hausdorff. So there you go. The quotient space is Hausdorff, So the quotient space formed by modding out the G orbits is Hausdorff if and only if this particular set K is closed in the product, all right? So this is a somewhat technical proposition, but it's used a few times going on. And anyway, I'm following Manetti pretty much verbatim. This is page 93 in there. So I will say this, there are some points I had a hard time following him in these sections, so I'm sure we'll get stuck on something here soon. Let's see here, next proposition, let G be a subgroup of the homeomorphisms where X is Hausdorff and pi is the canonical map. Suppose there exists an open set A of X such that the quotient map restricted to A is onto, so that means that A has got like a representative of each equivalence class. That's what that means. In some sense, A is, I would say it's a section, but that's not, when I think of a section, I think of something like cutting through each equivalence class just once. There's not that expectation, right? But there's almost that expectation because there is an assumption that A cuts through each equivalence class like finitely many. Well, this is kind of like that, but it's not exactly that. So G and G such that G of A intersect with A is non-empty, is finite. So I don't know if I've completely understood the intuition behind that statement yet. I think that would probably be key to understanding this section more deeply. Anyway, then, if you have those two conditions, then X by G is Hausdorff. So here's the proof. So let's see here. And so I'm just going to sketch what Manetti does here. I skipped a few steps down here mostly, but so if we take G is, this set of the G in the group which have G of A intersect A non-empty, and we suppose that's finite, then that means there exist finitely many G1 through Gn for which Gi of A intersect A is not empty, right? And so, okay, we're trying to prove that this is a Hausdorff space, right? So let's pick P and Q distinct, and then we can choose X and Y, which get you to P and to Q, because remember, we're assuming that A is a set such that it A is a set which contains representatives from every possible G orbit, right? So certainly it contains representatives which get map U to P and map U to Q from that assumption of surjectivity. And we are, of course, also assuming that P and Q are distinct G orbits, right? Which means that, well, X and Y have to be different. Yeah. Now, we assumed X is Hausdorff, and for any I1 through IN, we can use that Hausdorff to select open U sub I and V sub I subsets of X where X is in UI, and GI of Y. Remember, GI of Y can't be equal to X, so these are distinct points, so I can choose sets UI and VI which separate those points, right? And then I can construct, as does Manetti, U as the intersection of A by the intersection of all the U's, and V as the intersection of A by the inverse image of all the V's, right? And I think if you sort through this, well, anyway, Manetti argues that U intersect G of V is empty for all G, and excuse me. I think if you look at this, you can see that P is in here, because, let's see here, X is in every single one of them, and so X must be in the intersection of this. And if X is in the intersection, it must be in the total intersection. So X is in U. I shouldn't say that. I should say P is in U, rather, because, well, oh, I'm sorry, guys. I've gotten lost in the mess again here. But I'm pretty sure that if I could sort through the mess of language here, that the point of this is just that these two sets have P and Q in their disjoint. So, let's see here. So, if GI of Y is an element of VI, then the inverse image of GI of VI contains Y. So, and there's an intersection I have somehow dropped. I'll try to get it back. This is probably going to be too fat. Intersection. There we go. Haha, I made it. Anyway, so I think that the well, all right, maybe these aren't the sets which separate. I think these are in the wrong place, because A is A is a subset of X, right? So these can't be subsets. These can't be the subsets which separate the pi and the I don't think that the U and the V so constructed can be the subsets of the X by G, which show that, you know, we're separating P and Q, right? That can't be the case, because they're the wrong kind of sets, right? These are points in X. So maybe it's that pi of U and pi of V give you, and remember the quotient map's an identification here, so the image of open's open, so pi of U and pi of V. I'll just, I think that maybe is what's going on here, pi of U. And so P is, I'm missing some pi's in here. I believe we can see that P is an element of pi of U, and Q is an element of pi of V, with pi of U and pi of V intersecting. They don't meet, okay? The reason that P is in pi of U is because X is in U and pi of x is equal to p, which means p is in pi of u. And likewise, you can argue that y is in here, therefore pi of y, pi of v contains pi of y, which is q. So p's in here, q's in there, and they separate. So therefore it's Hausdorff. All right, anyway, sorry. I'm going to move on. Let's see here. So example 1. Example 1 here, we have G. So this is not projective space, but it's just like token other example. So here it is. Let G be the group of translation by vectors with integer components in Rn. All right. So in other words, G is like phi from Rn to Rn, where phi of x is equal to x plus z, where z is a an element of the n-fold product of z with itself, right? So all the components of z are integers, right? And so you can form the quotient space Rn by G, and we can show that Rn by G is Hausdorff. So if you consider A to be the subset of Rn, which is given basically by the absolute value of components being less than 1, so it's going to be a, you know, I think A is technically going to equal, goodness gracious, I think I can say this without getting into trouble. I believe you could have just said A is equal to the minus 1 to 1, right? Minus 1 to 1, the n-fold product of that, right? Because that's how you get absolute value less than 1 for all the components in that hypercube. Anyway, so notice he says notice that pi from A to Rn by G is surjective, right? I think that's fairly clear because you can definitely take any point in Rn and you can divide off the integer parts and just leave like the decimal expansions of the points, and every decimal expansion is going to have a magnitude of at most 1, which means it fits in A, you know. So I think you could say that Rn by G is a lattice where A is a fundamental region. Actually, I think I'm wrong about that. I think that's actually not quite true, because this is false. This is false actually. This is what I was thinking, but as I went on and I studied these notes more, I've come to the conclusion that that's not the case. Not quite. See, a fundamental region, not quite. A fundamental region should be one which has just one. Not quite, too big. The fundamental region of a lattice should be a subset of, you know, the space which is forming the lattice, where you have one representative of each equivalence class, you know. And in A, I have more than one representative of the equivalence class generated by G here. So it's not a fundamental region. It's a little bit bigger than a fundamental region because it's got a few representatives, you know, for each equivalence class, but not infinitely many either. And so I think that's why it fits back into that pattern of that thing we saw back on page 3. It's kind of like this, you know, G intersect A, G of A intersect A is non-empty finitely many times. All right, so we'll actually kind of see that in a second here. But so anyway, not a fundamental region. I'm wrong about that. But anyway, so he says if Z is in Zn, we can take A. So what is the action of the group of homeomorphisms on Rn look like here? It's A plus Z, right? Where that literally just means add Z to the components of A. Yeah? And so that's non-empty only if the absolute value of AI is less than or equal to 1. guess I believe that. I kind of want it to be wrong, but only if, I mean, well, I think it's true. But anyway, so by proposition on page 3, which I just showed you a second ago, we find that Rn by G is Hausdorff because there's finitely many Z's for which that happens. Now, corollary, let G be a finite group of homeomorphisms of a Hausdorff space, then X by G is Hausdorff. So you apply proposition 3, taking A to be the whole thing X, all right? And my remark, so I said GA intersect A is not empty for finitely many G. Okay, so I guess it's okay. It's just, here are the G's which it happens for. Like so here's a picture of, A, not exactly, but you know, A would be inside, shaded in here, right, without the edge. And so if you take, for example, minus 1/2, make sure I can see it. If I take minus 1/2, 1/2, well, I can add 1, 1, and I'm still in there, right? So it's not a fundamental region because I can shift by something in the, you know, the lattice. I can shift by the group, and yeah, I'm back in there again. And anyway, so not a fundamental region, fine. But also, I think the only way you can start in A and then translate from A by an integer, and then have yourself back in A again, is if you're looking at G as either 1, 0, minus 1, 0, 1, 1, minus 1, 1, or 1, minus 1, or minus 1, minus 1. Hopefully I got them all. I mean, of course there's the identity, right? You know, A intersect A is A again, so there's always that. But yeah. Now I thought this was the torus, but I don't think it's exactly the torus. I mean, well, anyway, I thought it was the torus, but I think not actually. Well, I feel like you could find a torus, but it's not clean yet. I mean, the torus, I believe, is taking those identification pictures and just identifying the top and the bottom and the sides. But, all right, anyway, let's just move on here. Projective space, then. Excuse me. Here we go. So, oh man, I don't know if I can say that. Homotheties, or dilations, there we go. On Rn plus 1 are mappings that are just rescalings. All right, so you have phi of x is lambda x for some lambda, which is non-zero, right? So it's just a rescaling of the vector, right? And so if you think about that, rescalings, they're going to move points on a line through the origin to points on lines through the origin, right? So you can form, if you get rid of the origin itself, then you got a partition by these, the images of these dilations. Well, anyway, the point is that x is equivalent to y by one of these dilations is the equivalence classes are lines to the origin. But if I don't throw out the origin, then all of the equivalence classes meet at the origin, and then everything's equivalent to everything else, right? So you got to throw out the origin, otherwise it doesn't quite work. So throw out the origin, then all of the lines that go through the origin are the equivalence classes of the georbits here, and so x is equivalent to y equals x is equal to lambda y for some non-zero real lambda. And then you give this space, which we call projective n space, we give it the quotient topology. All right. So the georbits are lines through the origin with the origin deleted. And the notation that's commonly used here is this bracket x, 0 through xn is, the points in our n plus 1 that are, rescalings of x, essentially. You could put the lambda on either side, don't matter. Just 1 over lambda over there, same difference. But the lambda has to be non-zero. All right. And the quotient map is just pi of x is the equivalence class generated by x, right? And this is an open identification. And we can look at the inclusion map from the n-dimensional, the n-sphere, which is a subset of our n plus 1 with that, right? So let me just tell you where we're going. Like, he starts by defining projective n space like we just did, but not being content with that, he's going to redefine it, I think, in terms of n spheres. And this is, depending on what book you open, you might find projective space defined in terms of n spheres, or you might find it defined in terms of our n plus 1. Because you could do it either way. And that's kind of what this math we're going over right here shows you. So the n sphere, because the n sphere, it's still more than you need, technically speaking. I mean, so like, how am I saying this? Every line that goes through the origin cuts through the n sphere in a point in its antipodal point. So there are like 2 points in Sn for each equivalence class over here with respect to the dilation g orbits, the lines through the origin. And so on the other hand, so in Sn, this pi prime is this equivalence relation is the antipodal equivalence relation, which is that x and y are equivalent if y is equal to plus or minus x. So that's what this pi prime is here, and this is a commuting diagram, I believe, although I haven't defined what f is, but and he just says, suppose f is an open bijective continuous map, and it's like, he says, I think he says, assumes f is a continuous bijection. He doesn't give you a formula for f on this page in section 5.4. He just kind of like starts talking about it, and it's like, well, what's f? At first I thought that Manetti was defining f and f inverse by the diagram, and that's in some sense true, but I think what he's actually doing is using the universal property of identifications, which gives the existence of such a map. So if you go back to the start of the quotient map stuff, remember we had this particular theorem about the existence of a mapping. I think it was lemma or proposition 5.6. I think this all rests on that ultimately, but it doesn't matter, because on the next page I actually construct a formula for f, and just try to look at it directly, because I don't know, I spent a while trying to read that paragraph, and like it felt like I was not getting anywhere fast. And I know it's something simple, and it's just the identification universality stuff that I just don't have hardwired into my brain. So I decided to go back to base principles and just try to prove that these two were homeomorphic directly. So like, what's the homeomorphism of Sn by its antipodal equivalence and projective real n space, right? Which I'm going with this being defined as we did. I think the other thing I'm running up against is when he says things are identified, he takes them to be equal in some sense, whereas I don't do that by default, and so I'm looking for objects to be the same type, and when they're not, it weirds me out. So you gotta just be aware that he's a little bit more sophisticated in his use of identification than I am. Like, I like to write down a map between the things that are different and kind of sort it out, which will slow you down, right? It'll slow you way down if you're looking for a map and the author doesn't have a map, and then you can't make sense of it without the map. It'll slow you way down. But anyway, let's get back to my argument here. So I'm defining the potential homeomorphism from this space to that space by, I take my antipodal pair and I map it to the equivalence class of x. Now you say, hey, there's two representatives. How you can use that one and not that one? Well, I can, because the equivalence class of x and the equivalence class of minus x are equal because x is related to minus x. Just take lambda equal to minus 1, right? So this is a well-defined map, and you can also prove that it's onto. If I have a, an equivalence class in one of the points in projective n space, which would be bracket x, then of course x is not equal to 0, and as such I can rescale it, right? I can normalize it. I can put a hat on it, make it length 1, right? So this is mapping r of x is x divided by the norm of x, right? That gives you a unit vector. And of course, the other relation that you should remember from calculus 3 is any vector can be written as a magnitude times a direction. Here at b, and I had a residual extra hat there. Let me get rid of that one. So I could either write r of x or x hat. I wrote r of x some because x hat's just my nostalgia for calculus 3. It's not actually a Manetti. But that is what r of x is the hatting of vectors. Anyway, so any vector is a magnitude times its direction, and you can easily see that phi of the antipodal pair r of x comma minus r of x is equal to the equivalence class of r of x, which by this formula right here is the equivalence class of x, right? Because you just take lambda equal to the norm of x and they're equivalent, yeah. So anyway, phi is onto, and to see that it's 1 to 1, suppose you got that equal to that, then it means the equivalence class of x equals the equivalent class of y, but that means that y is equal to lambda x. However, that means we notice that we've got norm of x equals to norm of y, right? How do I know that? Well, I know that because the norm of x and the norm of y are both 1, because they're taken, here x and y are pairs that are from the antipodal pairs in Sn, and those are pairs of points. X is an element of Sn, which means the norm of x is 1. So this is more to the point, that's equal to 1, right? Let me put that in there. 1 equal to that, all right. And so we also know, of course, that you can take the norm of this relation, and by properties of the norm on Rn, we've got norm of y is the absolute value of lambda times the norm of x. But these are both equal to 1, which gives me the absolute value of lambda is 1, which means lambda is plus or minus 1, which means that y is plus or minus x, which means that these two antipodal equivalence classes are, in fact, the same. Therefore, phi is 1 to 1. Thus, phi is a bijection. And then to argue that that bijection is both continuous with continuous inverse, I think then we could fall back on the diagram back over here and come to terms with, like, where is, f is here, and I can get continuity of f by, noticing that, it has the necessary relations with other continuous maps that are at play here. So I don't want to get into all that because my mind's not quite clear on it, but I'm pretty sure that's all there is there. And to make that actually happen, to prove the continuity of f easily, you just have to make use of the theorems of continuous quotient, like the maps about the continuity of the quotient map and the continuity properties of the identifications and all that, all right? Or I suppose if you were just a brute force, kind of person, you could just try to prove directly that this mapping is continuous with continuous inverse. I don't want to do that. All right. Anyway, so we find, if you'll forgive me for not proving the continuity, that phi is a homeomorphism. And all right, great. Then notice that the homothesis. Okay, so the homeomorphisms in the group that define the equivalence class, the antipodal equivalence, are just plus or minus identity maps. So of course that is a finite group of order 2, and as such that makes, and since Sn is Hausdorff, we've got a Hausdorff space mod a finite group, and that is Hausdorff then by the previous theorem that we had. And since that's Hausdorff and homeomorphic to the projective n space, it follows that projective n space is also Hausdorff. So going forward past this point in the book, don't be surprised if he just basically claims that this is projective n space. See, like once a topologist proves that two spaces are homeomorphic, they have this habit of just identifying them and saying that they're the same thing, So I think that happens in this section. I think there are places later in the section where you can see he's not thinking of projective n space as being a set of equivalence classes in Rn, defined from Rn, but rather a set of antipodal pairs. All right, anyway. Example 3, if you take the two disk, x is equivalent to y, if and only if x equal to y, or you're on the edge of the disk and you've got antipodal, he's basically identifying antipodal pairs on the edge of the disk, right? Then this is, if we use this equivalence, that is yet another way to look at projective 2 space here, I believe. Because the way it works is this: you can take the D2, that's homeomorphic to, like, you can just imagine kind of like imagine a rubber sheet and just blow it up into a half a sphere, right? Well, that's a homeomorphism. Here's the formula. This maps to that, and that maps to this, and the equivalence relation that's described on D2, when you kind of just map it over to here, you get that each point on the upper part of the bubble is equivalent to itself, just like every point in the interior of the disk is equivalent to itself and itself alone. But then you also have the equivalence of the antipodal pairs on the equator of the upper hemisphere here. And then since the upper hemisphere is half of the 2-sphere, you can include it in the 2-sphere. And then it's got, it's got a it meets each g-orbit of the antipodal equivalence on the 2-sphere. It meets each orbit at least one point, right? It's got at least x for minus x. Excuse me. And as such, sorry, I just polyurethane my table, and my polyurethane fumes always get to me a little bit. Let's see here. All right. But Matthew broke his arm, and he'd taken his cast and he like scrubbed the finish off the table. I had to refinish the table. Anyway, it's okay. So here's goodness gracious, sorry guys. So here's the relation. You include the upper hemisphere in the 2-sphere, and you've got projections under the antipodal equivalence, right? Either the full one or the restricted one. And anyway, it's a commutative diagram of continuous maps, and here J is bijective, so it maps a compact space X to a Hausdorff space P2 P2R. And X here is like the D2 mod the equivalence class, so that's why it's compact. Compact continuous image to Hausdorff space, that means that J is in fact a homeomorphism. So there you go. That's yet another way to look at projective 2 spaces by quotients of the disk by this equivalence, right? So there are, in low dimensions, there's a lot of different ways of looking at a particular projective space, yeah. And then finally here, well, not quite finally, here's another one. And this right here, I think we don't really need too much, but if we were going to talk about projective space as manifolds, these are coordinate charts on projective space, if I remember right. So he basically lays out these sets of equivalence classes such that the ith component's non-zero. That gives you an identification cover. And if you look at the projection map, the inverse image of these A's, it's like all points in deleted n plus 1 space that have a non-zero x sub I not equal to 0, which is fairly clearly open. It's the union of two open half spaces, and then he defines F by just putting a 1 in the 0th spot, and so that is a bijection with inverse, which when you compose to the pi has this. So if we f inverse composed of pi of x0 through xn. We just take x1 over x0, xn over x0. And yeah. So let's see here. That makes sense, of course, because A0 is exactly the space which has non-zero, zeroth components, right? And anyway, so like if you're working with projective n space and you want to look at it as a manifold, it is an n-dimensional manifold because it is homeomorphic locally to Rn. And if you look at like all of the representatives of the projective n space, you can always you can piece it up into, you can split it up into pieces where you have a particular particular, what's the word, sorry guys, words, component non-zero, right? And so I don't believe we have a global coordinate chart usually. I don't think, maybe ever, except possibly in like a really low dimension. I'd have to think about it. But you can string these together, and you can put n coordinate charts which cover all of projective n space like this. But anyway, if you don't know what a manifold is, that's all good. Let's just go on here. So finally, the other kind of projective space that's of interest for Manetti is complex projective space. In complex projective space, you define pretty much the same way. You look at 2 points being equivalent in complex n+1 space if they're related by a non-zero complex multiplication. You form the equivalence by the g-orbits of that, and then you give Pn(c) the quotient topology, which is naturally defined there, and that gives you projective n-dimensional, projective complex projective n space is what we usually say. Sorry, words escape me today. Projective spaces, both complex and real, are connected, compact, and Hausdorff. And so here's where I was talking about all of a sudden he's dropped his definition and he's just using his theorems and replacing Rn+1 with Sn. He's like, well, Sn, the projection from Sn to Pn, and the projection from S2n+1 to Pn. So S2n+1 you can characterize. So the odd spheres we can look at as particular subsets of complex n+1 space. See, because this would be real 2n+2 space, and so you would need R2n+2 to look at the 2n+1 sphere, right? We need R3 to look at the 2 sphere, for example. So R3 could also be looked at. Excuse me, we need R4 to look at the 3 sphere, right? So the 3 sphere could also be looked at as a particular subset of C2, right? It would, the norm of Z to be 1. All right. Anyway, so these projection maps, he doesn't tell us exactly how to define them. You can guess. They're continuous and onto. I think I know them. They're the ones. These are the antipodal map, right? Like, well, anyway, it's basically just, well, I don't know. I kind of think of these as sort of a restriction of the, Rn+1 or R2n+2, those spaces can be restricted to these spheres, and in so doing you still have at least, you have 2 representatives for each equivalent, 2 representatives for each of the equivalence classes in the projective n space. Yeah. Anyway, let me get to it here. So since the projections are, and maybe I should say they're the restriction of the projections to these guys, right? It depends on what I mean, I guess. But anyway, the point is that the n spheres are compact and connected. And if you got a continuous image of a compact and connected space set, it itself is compact and connected. So that proves that the projective n space is compact and connected. To see that it's Hausdorff, we already proved that real projective n space was Hausdorff. To see that the complex projective n space is Hausdorff, we'd have to study the K, which is, the subset of Cn plus 1 without 0, Cartesian product with itself, like that. And so here's like a really quick reason, and this is, I would say, is it a theorem? I don't know if it's a theorem, but I have a hard time coming up with a counterexample to it. So let me just tell you this. If you're looking at a set in some kind of Euclidean space, and it's defined by an equation, right? But lambda's that's any lambda, isn't it? Huh. Ooh. Oh, it's not obvious to me then. Never mind. I was thinking I could say it's defined by an equation, so it's closed, but the fact that lambda is a variable there makes it... I guess it's still an equation if I just include this lambda as part of my space. But he's got about a half a paragraph where he explains what this means in terms of if you identify this as column vectors and then look at it, well, this is something about minors of 2 by 2 matrices, and therefore the set is closed. It's not immediately obvious why this set is closed, I guess. Except that it's defined by an equation, and usually those things are closed. And if it was defined by an inequality, I'd be tempted to think it's open. So, for example, SLNR is defined by determinant, determinative matrix equals to 1. That's a closed set, whereas GLN, GLNR is open because it's defined by an inequation. It's defined by determinant positive or negative, right? Which ends up being open, and then the determinant is continuous, so the inverse image of an open set union another open set is again open. We've talked about that before, I believe, but anyway, hey, that's it for here. I was hoping to recycle some of the I really wanted to recycle some of the videos I have from Manetti back in my first time through Manetti back in 6 years before this, right? Back in 2016, I think it was. But unfortunately, like, the audio quality in that's not so good, and well, I really wanted to recycle it, but I just, it's not quite right. So anyway, I'm going to write up the next one. Should be on sequences, and so hopefully we'll get to the end here before the end. Working on it, one bit at a time here, guys. Maybe there's a chance I can recycle my lectures on homotopy and things. I think my lectures on homotopy from the topology analysis class might be actually worthwhile. Unfortunately, I think I use Gamelin's topology there and not Manetti, so maybe I can't do that either. Anyway, I'm working on it, guys, so just bear with me here. Thanks.